Everyone, and thanks for having me. Just gonna move this out of the way. So I'm Kate Follette. I'm an assistant professor of astronomy at Amherst College, which is in Western Massachusetts. And I've been tasked with talking to you about accretion onto planets and circumplanetary disks. This is the abbreviated version of what was already only a subset of results in this field. And so I certainly won't do justice to it. But I will give you some highlights, and I'd like to highlight in particular some of the work of my students, some of whom are pictured on the bottom here. And I would also like to take an opportunity in this forum to mention that at Amherst College, we are hiring this year. And if you're interested, I think it's a great place to work, and I'm happy to speak with any of you about what it's like to work here. So please reach out by email if you have any questions. So the full version of my talk is available on the Sagan Workshop YouTube channel. I'm going to give very abbreviated versions of the first two parts of the talk that I gave in full. So kind of the basic outline is, why you should care about direct imaging. This in particular is one that I'm not going to belabor right now, because you've heard we're in the last day of the workshop now, and hopefully you've heard a lot about direct imaging and are already converts and convinced that it's interesting and important. I'll also talk about 4 reasons why accreting protoplanets in particular, so the youngest directly imaged planets, are hard to study. And then I'll give you an explanation for 3 things that I think are going to be really exciting. Probably many of you are working on these things right now. So I'm skipping straight to the conclusion of my 5 reasons to care about direct imaging. We can see planets. By seeing them, we can characterize their spectra directly and characterize their orbits as well. So shown on the inset here is some work by my student, William Balmer, who's now a grad student at JHU. By virtue of the fact that directly imaged planets are only detectably bright when they're very young, we're detecting them in their infancy, or in some cases, I don't know, that they're natal, right? They're still being formed. We also, for those of us like me, who are interested in planet formation and, sort of the pre-planetary stages of stellar evolution, directly imaged, in particular protoplanets, are extra interesting because they tell us about how planets that are newly formed interact with their natal environments. So those are 5 whirlwind reasons why you should care about direct imaging. So on to this piece where I'll explain to you why it's hard. So one thing that's really struck me in recent years is that all the stages of this sort of classic picture of how you go from a molecular cloud to a fully formed planetary system, at the coarsest level, all of these stages have been observationally verified. We know that we have thick protoplanetary disks that get dispersed, and we know we have lots of mature planetary systems, but kind of the gap between the stage on the very bottom of this schematic and the one on the bottom left is kind of still a mystery to some extent. So how do you form planets from that disk, and where do they form, and how do they evolve? So historically, the way that this has been tackled is to take really high resolution, high contrast images of disks and look for signs that planet formation is actively happening in these young disks. So I'm showing on the right here a preview of a gallery that we're preparing for a Protostars and Planets chapter that's being led by Miriam Benisti, just highlighting all of the complex and beautiful morphological features that we see in young disks. These are all near infrared images from Gemini, Subaru, and the VLT. And the thing about these structures is, as beautiful as they are and as ubiquitous as they are, Sean Andrews, I think, in his talks often mentions how, every time we get higher resolution images with ALMA, we see even more substructures. It's just substructures all the way down. that even though we have all of these and they're very well documented, they happen across spectral types, it's really hard to take a feature. If these are signposts of planets, they're really confusing ones in the sense that we have yet to really be able to say, okay, this substructure has this nature and it tells us there's a planet at this location and we can verify the existence of that planet. Those kind of cases are few and far between, and in some cases sort of debated. So, the ideal here is obviously to look for the planets themselves instead of trying to infer their existence from disk substructures. But this really isn't easy. So this is another part where I'm gonna condense what I broke out in a lot more detail in my longer talk, to just say that the first two obstacles to detecting protoplanets are that they're faint and they're close. And really, really close compared to other directly imaged planets. So this is just kind of a gallery of published images of so-called transitional disks, which, if a classical circumstellar disk, protoplanetary disk is like a pancake, these are like a donut, right? They have a big hole in the center. And that hole is approximately solar system sized, which is very evocative of ongoing planet formation, sort of clearing these central cavities. So this is kind of one of the places, maybe the primary place that we look for protoplanets. But these cavities are tens of AU, and they're 140 parsecs away in general in the nearest star forming regions. So that's a factor of about 3 times farther away than most directly imaged planets, which are within 50 parsecs. So this translates to something like 1/10 to 1/4 of an arcsecond is the size of the cavity we need to resolve within that in order to find protoplanets. So that's one obvious reason why it's really difficult to do this work. The sort of saving grace thus far has been that these accreting protoplanets happen to be very bright at H alpha. So they're emitting very brightly at 656 nanometers. This is a plot from simulations by Christophe Mortacini and company, and it shows planet mass on the x-axis and the ratio of the luminosity of accreting protoplanets at H alpha to the luminosity of the sun. And the basic idea here is, the very upper envelope of these, which, is on the far, so this red region sort of in the central right-hand side, these are objects that are, by the way, the color scale is the accretion rate with the highest accretion rates at the top. So these are objects that are very massive and accreting very rapidly. And if you kind of read over to the left-hand axis, the contrast between the luminosity of these objects at H alpha and the sun at H alpha are on the order of 10 to the 3, 10 to the 4, so 1 part in 1,000, 1 part in 10,000. That's about 3 orders of magnitude, 2 to 3 orders of magnitude brighter than the planets that we directly image in the near infrared. So we have to work really close in protoplanet direct imaging at H alpha at least, but we can detect planets, but planets are a little brighter, I guess, is the upshot. So this is basically what it looks like if you want to image something at H alpha. So we have subtracted the light from the central star and just replaced it with a cheesy yellow X here. So this has been subtracted to remove the starlight. And you can see there's a sort of interesting blob to the bottom right of the star here. The trick with this imaging technique is that it's a differential imaging technique. So you take images simultaneously at a wavelength where you expect the planets to be bright if they're accreting, and at a wavelength where you expect them to not be bright, and then you subtract the two. And the idea is that protoplanets should kind of pop out. Here's the thing about that. So that all looks like a really clean story, and this looks like a nice detection, but it's not this easy. So I should say that this protoplanet candidate is pretty controversial. And don't worry, there are some uncontroversial ones that I'll show you in a bit, but why is this a controversial detection? Well, the third thing that makes detecting protoplanets really hard is that they're embedded in disks. And we use very aggressive processing algorithms to remove starlight from our images, right? It's very difficult to image extremely faint things next to extremely bright things. And so we have to use these algorithms. And in particular, we use algorithms that do a form of principal component analysis. So I'm going to show you a plot here where there's a relatively simple system that has just an M-dwarf companion. So it's a star with an M-dwarf companion at, about 1/10 of an arc second. So at about the same kinds of separations we're talking about for other transitional disks. So this should really be a slam dunk detection. And it's a heat map. So each pixel here represents a reduction. Same data set, apply a different set of algorithmic parameters for a starlight subtraction algorithm. And the parameters themselves are on the X and Y axes, but their nature is not so important here as to just say that there are actually 25 tunable parameters in these algorithms. And this one happens to be, these two happen to be some of the most influential. So every pixel here is an image where we've pulled out the peak signal to noise of this known object in the image. So there are regions of parameter space here where you get really beautiful detections. There are regions where you still get detections, but they're not great. And then there are regions where you can kill the signal from even this very, very bright object completely. So what's the takeaway here? Well, we use these computationally intensive algorithms, operating at wavelengths of light where the atmosphere is very poorly behaved. So every data set is its own sort of special thing. And the results that we get are very highly dependent on the choices that we make in the algorithms. And I'll just show you another version of this with, in this case, a transitional disk that has a couple of protoplanet candidates. So this is, again, same data set, except in this case, it's reduced with different versions of starlight subtraction algorithms, getting kind of increasingly aggressive as you move from the top to the bottom. And what you'll notice is that for these unaggressive techniques, the sort of top row, you see very robust structures, but you also still have a lot of starlight. Like if you're not aggressive, you're not removing much starlight and you're not imaging the inner regions. As you get increasingly aggressive, you reveal more and more structure closer and closer to the star. But you also tend to turn continuous structures into things that look like points. So this is one area where my group has been doing a lot of work trying to kind of validate and test these algorithms. So stay tuned for my student Jaya Adams' paper coming out later this year. So PDS-70 to the rescue here. Not all of these protoplanets have confusing disk structures close by. And in fact, PDS-70 has a beautifully wide cavity such that we can detect, you can see the cavity in polarized light here from Miriam Kepler's 2018 paper. But it's sufficiently separated from its star, and the cavity within this transitional disk is sufficiently cleared that we can detect this even in the infrared. And in the infrared at a bunch of different wavelengths at L band, at H, K, and several epochs for L and H. So it's there, it's robust, it appears at multiple wavelengths. We've also imaged it at H alpha. So this is a paper that Kevin Wagner led in 2018, where we detected the companion at H alpha as well. So it's accreting from within this transitional disk gap. Okay, great. So this is the poster child. It has rightly, I think, become the poster child for protoplanets because I think it's the only uncontroversial of the protoplanets that have been put forward. Because it is as robust as it is and as well separated and as bright as it is, I think this is actually kind of a thing I'm excited about, but with some of the like new generation of instruments behind very large telescopes, we are able now to resolve, sort of get very low resolution spectra of objects like PDS 70b. So you can see some work with gravity on the VLT from Jason Wong, and with Muse also on the VLT from Haffert in 2019. So we can resolve some parts of the spectrum, and with Muse, we can actually even resolve the emission lines, the H-alpha line, and use it to characterize accretion. So I think that's a really exciting thing moving forward. So now some more of the dirty laundry, which is the parameter we're actually interested in is not the brightness of the planet. It's not its ratio relative to the central star. It's accretion rate or its growth rate. So if you want to take the actual observation, which gives us the ratio of brightness of the planet to the star, and turn it into an accretion rate, it requires a horrifying, honestly, set of assumptions. Many of these have sort of sub-assumptions under them. And one of the principal assumptions is that accretion onto these protoplanets behaves just like accretion onto stars. So I'd like to unpack that idea a little bit here by telling you a little bit about what we know about accretion onto stars. You've heard some about this week, I think. So this is a classic plot of object mass versus mass accretion rate, where some excellent students of mine have collected basically all of the results that we could find in the literature of mass accretion rates for objects. And here are all the stars. So they lie along a relation that's approximately a power law with a power of 2.1. But as you'll notice, there's significant scatter in the relation. So one thing we kind of set out to answer to start was, how well do we understand this? And in particular, how well do we understand this? How well does this pattern hold at substellar masses? So here I'm putting some brown dwarfs on here, and you can see they follow basically the same pattern. So that's good. To explain the scatter, I had a student recently do a really excellent undergraduate honors thesis looking at the sources of this scatter, and I'll sort of gloss over a lot of the interesting results and just say he found that you could explain almost all of the scatter with a combination of observational uncertainty and two physical parameters: the age of the object. So I'm showing a plot here. This is the same plot I'm going to be showing for the next several slides, same one that was on the last one, where the objects here are colored by age. And he found that if you took a best fit slope, a best fit line as a function of age, you can see basically exactly what we expect, which is as these objects age, their accretion rates decrease. And so that results in some scatter, some vertical scatter in the relation. The other physical effect that we expect to contribute to this is variability. There's no reason to think that accretion onto stars happens in a completely steady, non-stochastic process. So we know that there's variability. So this is just to say that, glossing over a lot of detail, between observational uncertainties, variability, and age, we think that we can describe all of the scatter in this relation. But I glossed over something here before, which is that these cyan points I've put on here are only isolated brown dwarfs, so free-floating brown dwarfs. What if you put the planetary mass companions on? Well, here are all of them, not sorted by how widely believed they are. And it's sort of evocative here of maybe a different relation. So in particular, there's no reason to think that planets form like stars as small clumps in a molecular cloud that just happen to form and end up being bound to stars. We think they form in a disk. And in particular, if you have a gravitationally unstable disk that fragments, you expect a sort of flatter relation in this mass accretion rate space than you do for sort of conventional star formation. So these are evocative of that, but very problematic because Even our individual estimates for their accretion rates vary. So in this case, these faint pink points that are connected by dotted lines are all different measurements from, in most cases, the same paper for the same object, where I've just plopped the dark pink point is the average. So if you plot the averages, it looks really evocative. If you plot all the different values, sort of taking into account all of our uncertainties, it's a complete mess. And there are lots of possible explanations for this that I think we're going to need to answer in the coming, I don't know how long it will take, coming years. So just to summarize the 4 obstacles, planets are close and they're faint. They're embedded in disks, which makes disentangling their emission from disks very complicated. And they're hard to interpret. So what am I excited about? Well, the first one is very much related to what I was just talking about, which is that I think we can understand substellar accretion. Probably the best first step that we could take is trying to understand what accretion looks like for substellar objects at multiple wavelengths. So the first kind of thing, the first idea here is basically related to the set of assumptions that I showed you for lit calcium-15. If any one of those intermediate assumptions is wrong, and in particular, if our assumption that we can scale H alpha luminosity to total accretion luminosity to accretion rate, if that assumption is wrong, then we're going to get the answer wrong here. We're basically applying the wrong scaling law in getting these. So what do I mean by this? I mean that the relation between H alpha luminosity and accretion rate was established for stars through decades of painstaking work building up multi-wavelength spectra of accreting objects. So here's an example for an accreting star, BP tau, where the gray spectrum is the observed spectrum and the blue spectrum is a non-accreting object of similar spectral type. So the quantity that's actually correlated with accretion rate is the total accretion luminosity, the excess emission from the accreting object at all wavelengths. And that happens to scale relatively well with single wavelength tracers, like H alpha, for stars. But is that the case for planets and brown dwarfs? And is the relation the same? I think that remains to be seen. So this is the picture of accretion onto stars. We think we have a decent understanding of where the different components of that spectrum come from. And I know I'm running a little short on time. I want to leave time for questions, so I'll gloss over this and refer you to my talk, which is just to say that if you wanted to really estimate, if you wanted to establish scaling relations for the substellar regime, you have to have multi-wavelength detections. You can't just have an H alpha detection or even just infrared detections. Really, you need to go to the UV because the principal source of accretion luminosity is the hot spot on the star, which is emitting like a black body at a much hotter wavelength than the star itself. The UV is kind of the best place to trace that emission. So I was very excited to see this paper by Yifan Zhou with a detection of PDS 70b at UV wavelengths. But this is kind of like the brightest possible point in the UV. And it will be awfully hard to piece together the rest of this, this spectrum. So basically everything that's not 656 nanometers and this one UV narrowband feature. So our philosophy in my group has been that what we should really do is try and get as many multi-wavelength observations of accreting brown dwarfs as we can, and in particular planetary mass brown dwarf companions. So I have a number of excellent students who are working to piece together data from UV to optical wavelengths with Keck and near infrared wavelengths with SOAR for as many of these planetary mass companions as we can, to try and kind of develop accreting templates for lower mass objects and test these scaling relations. So stay tuned for that as well. I'll go real quickly through these last couple, which is once we detect protoplanets, the other really exciting thing is they have their own accretion disks. There are circumplanetary disks. And this is again, PDS-70b to the rescue, or C actually in this case. So these are ALMA observations of PDS-70, where the C component has a very convincing circumplanetary disk detection. And Miriam timed this perfectly because yesterday this image was released showing new, even higher resolution ALMA imaging of this system that's just beautiful and reveals at even higher resolution that there really is an excess of millimeter emission at the location of the PDS-70C planet. So these are, you know, sort of moon forming disks that'll be really interesting in sort of constraining how planet evolution proceeds once a planet has cleared its disk. And we have a few other sort of signatures, sort of indirect signatures of accretion onto planetary planets and the sort of population of circumplanetary disks. So some evidence that there might be kind of streamers of material. Again, I'll go real fast through this. And then another really interesting and what's proven very fruitful technique of looking for these kinks in the velocity channel maps from the ALMA detections that reveal sort of structures. These kinks are basically well reproduced by models where you have a planet embedded. And the exciting thing about it is that the sort of maximum deviation that you get from the Keplerian velocity in these cases should track reasonably well with the mass of the planet. So this might be a way to weigh protoplanets without directly observing them. I'm not going to go into future technologies and instruments, except to tell you there are a bunch of really exciting ones coming up. So I'm going to go to my conclusions here, which is just, I hope I convinced you that direct imaging is by far the best way to detect planets, or at least to characterize planet formation as it's occurring. And at the same time, you know, we have a lot of work to do in learning about how to interpret the signatures of protoplanets that we're detecting. But there are a lot of exciting prospects for doing that, ways that we can characterize their disks, characterize them at multiple wavelengths, probe the accretion paradigm, and maybe even weigh them with the millimeter emission. So thanks very much, and hopefully I have time for a question or two.
Thank you very much, Kate. Yes, we have a bit of time for questions. Actually, there are 3 of them that I find interesting and that are possibly can be merged together. Someone is asking why H alpha specifically, and someone else is saying, like, apart from H alpha, are there any other sharp emission lines that could also be observed and could help reinforce the detection of a directly imaged accreting planet? And finally, there's another one that is asking if UV photometry would be a viable alternative to H alpha luminosity for discovering accreting planets. So I think these kind of 3 questions are somehow related and linked. We can maybe make a global answer.
Sure. So let me just start here with. So are there other accretion lines? So why H alpha? H alpha, because it's the brightest, basically, of the emission lines. It's not the best. It can very easily be confused with chromospheric activity, but it's the easiest to detect. So it's purely based on that. At the same time, we do think that for brown dwarf companions, at least, instruments like JWST should be able to detect other emission lines. And the reason that is exciting is because if you get line ratios, you can probe more of the physics of the accretion process. So there are kind of alternative paradigms for how accretion is happening that suggest that, for example, you know, if most of the hydrogen emission for a star comes from the infalling accretion column because the surface layer of the star is too hot for hydrogen to be bound, for electrons to be bound to protons, but you're falling onto a lower mass object and the temperatures are lower and you do have bound electrons, you actually expect there to be like very different physics, because most of the line emission may be coming from the post-shock region as opposed to the infalling accretion column. And that could be probed in the line ratios. So I think there are lots of exciting prospects for other wavelengths.
Well, thank you very much. And it's 10 a.m. Pacific time, so it's time for a break. But maybe before that, Dawn or Elise would have announcements to make.
Yeah, I think we're ready to break. Maybe just one quick announcement about